Okay, today we are going to continue the study of groups. Just like for a set, we can define subsets, and for a ring, we can define subrings. For a group, we can define subgroups. So here's the definition. Let's say we have a group G, and let H be a subset of G, and which is also a group with the same binary operator as G. Okay, so H and G share the same binary operator, and with that same operator, H is also a group. Then we say H is a subgroup of G. And of course, H must be a non-empty set. Okay, if it's empty, then it's not a subgroup by definition. So basically, if we have a subset of a group, then to check whether that subset is actually a subgroup of G, then we need to check all the axioms of groups. But here's a nice theorem called Subgroup Criterion. Just like we had a subring criterion for rings. So here's the theorem, and let H be a non-empty subset of group G. So G is a group, and H is a subgroup of G if and only if for all elements A, B in H, we have AB is in H and A inverse is in H. Okay, so here this says H is closed under the same multiplication as in G, and this A inverse is the inverse of the element A, which is also, so if A is an element of H, then that means A is also an element of G, because H is assumed to be a subset of G. Okay, and this A inverse is the inverse of the element of A as an element of G. Okay, so in general, A if we just say H is a subset of G, A inverse may be out of H, but it's still an element of G, but it can be out of H. But if that is indeed an element of H, then the subgroup criterion is satisfied. Okay, so that's what this theorem says. So H is closed under multiplication, and H is closed under inverse operation. So that's the subgroup criterion. Okay, let's prove this theorem. Since this is if and only if statement, we need to prove both directions. So first, let's prove this direction, only if part. Okay, so suppose H is a subgroup of G. Okay, of course, the binary operator of H is the same as that in G. So since it's a subgroup, H is a group. So H is a group. Therefore, for all elements AB in H, we have AB is in H. So H is closed under multiplication. So this one is satisfied. And now we need to prove that we need to prove for all A in H, A inverse is in H. Okay, but as we have noted before, this A inverse is the inverse of A as an element of G. Okay, so in general, if this is G and this is a subset of G, then if we pick an element from H, then its inverse as an element of G may be uh, outside of H. But what this theorem says is that if H is a subgroup of G, then A inverse must be inside H, not here. So that's what we are going to prove. So what this means is that, let's say, since H is a group, okay, so we want to prove this. Since H is a group, for all element in H, there exists an element, let's call it A prime, such that A prime A is the identity element which is in H. But here again, this identity element, let's go identity element in G, we are not assuming that this identity element in G is also an element of H. So we are not assuming this. So we need to prove that too. So let's see. So we need to prove this part, okay? So since H is assumed to be a group, then let F H be the identity element in H. Okay, so instead of E we write here F. So A prime A is F, which is the identity element. So identity element in H. So F squared, consider F squared. We need to show that we are going to show that this F is actually the same element as E, the identity element in G. Okay, to show this, consider F prime. And since F squared, F is an identity element in H, F times F is equal to F. And as an F is also an element in G, so this is equal to F times E, since E is the identity element in G. So we have, after all, we have F times F equals to F times E. But since F is an element in a group, we have so F is also an element of G, so there is F inverse in G, right? So if we multiply F inverse from the left, then we have F equals to A. Therefore, this identity element in H is actually the same element, same identity element as in G. So we have, after all, so we can replace this F with E. So that means A prime A is equal to E. So if we multiply A inverse as an element of G from the both sides, from the right, then we have A prime equals to A inverse. Therefore, this A prime as the inverse element of A in H is equal to A inverse as an element of G. Therefore, this A inverse is an element of H. Okay, so the second condition, this one is satisfied. So that's the end of the only if part. Next we prove if part. So conversely, suppose so H is a non-empty subset of G, and for all AB in H we have AB in H and A inverse in H. So this is the assumption here. Now we want to show that H is indeed a group. To show a subset H is a group, we need to check all the axioms of groups. Okay, the first one is the closure condition. So that means uh, for all AB in H, we have AB in H. But this is an assumption, right? Here, by assumption. So by assumption, the closure condition is satisfied. And second is associativity. That is, for all A, B, C in H, we have A B times C is equal to A times BC. But this is true because this holds because A, B, C are also elements of G. And G is a group, so the associativity holds. So this is fine. And the third condition is the existence of identity element. So let's see. The definition of identity element is that let's see. So suppose A is in H. So the definition of identity element was E times A is equal to E. So there is an element such that if we multiply that element to any element, that any element remains intact. So that's the behavior of the identity element. So we want to find such an element in H. Okay, and let's see. So one of the assumptions is that A inverse is included is an element of H. So for any A, we multiply A inverse, which is an element of H. So if we multiply A inverse with A, we get E. Because A and A inverse, they are also elements of G. So if we multiply them, we get the identity element of G. Okay. However, because of the closure condition, A and A inverse are assumed to be elements of H, so that A inverse A is an element of H by assumption. Therefore, the result of which is E, is an element of H. Therefore, the identity element is indeed in H. So that's fine. And the last is the existence of inverse for every element. So that's guaranteed by assumption. So we just skip it. Here, assumption is for every element there is an inverse element. So that's guaranteed. Therefore, H is a group. And H is also a non-empty subset of G, so that H is a subgroup. And the proof is done. Here are trivial examples of subgroups. Let G be any group. The subset of G consisting of only one element, that is the identity element. This is a subgroup. Of G. And also, G itself is a subset of G, which is a group, of course. So these two are trivial subgroups. And we define the term called proper subgroups. Proper subgroup. A proper subgroup is a subgroup of, let's say, G that are not this, this, or this. Okay? So, of G is a subgroup of G other than the trivial subgroups. Is a subgroup of G other than this or G itself. And let's see an example of a proper subgroup. And let's say, as usual, G is a group. And let's say A is one of the elements of G. Okay, then let's define a subset H as the elements of G that can be expressed as powers of A to the power of n, where n is integer. Okay, then this is a subgroup of G. To see this, we apply the subgroup criterion. That is, what is it? So for all A, B in H, H is closed. AB is an element of H, and A inverse is in H. So that's what we check. So AM times AN, where M and N are integers. So as we have defined the powers of any element of a group, this is equal to A to the power of M plus N, which is obviously an element of H, because M times M plus N is an integer. So H is closed under multiplication. And what about the inverse? So AM inverse is obviously A to the power of M negative M, which is in, so since negative M is an integer, so this is still in H. So these two conditions are satisfied, so this satisfies the subgroup criterion. Therefore, H is a subgroup. And another example, let's say Q star. Consider Q star as a multiplicative group of non-zero rational numbers. Okay, so this is a group under multiplication, ordinary multiplication of numbers. And let's say H is a subset of Q star, that is the set of some squares of numbers, squares of elements. So U is an element of Q star, and U square is the form of the elements of H. Okay, then this H is subgroup of Q star. Okay, to see this, we again apply the subgroup criterion. Let's say if A and B are elements of H, then that means A can be expressed as a square of some non-zero rational numbers, and B can be expressed as a square of some non-zero uh, rational numbers. X and Y are non-zero rational numbers. Okay, so AB is x squared times y squared. That is, so these x and y are just ordinary non-zero rational numbers. So this is this. So and xy is a non-zero rational number. So square of that belongs to H. And also A inverse is x squared inverse, which is x to the power of negative 2, which is x to the power of negative 1, that is x inverse squared. Again, x inverse is an element, is a non-zero rational numbers if x is a non-zero rational number. So this belongs to H. Therefore, these two conditions are met, so H is a subgroup of Q star. Next, let's try to find proper subsets of this cyclic group of order 4. So any subgroup must contain the identity element, right? So we have 4 elements in the group, and suppose we have a subgroup that contains the element A. Is this a subgroup? So let's try to make the Cayley table for this. So this is A, and this must be E. But so if this is a subgroup, then this must be E. But what if you look at this table, A times A is C. So this means this subset is not closed under multiplication. So we need to add another element, C, at least. Okay, so let's add C. So this is C, this is C, and AC, then this must be E. AC, this must be E, and this must be. So if this subset EAC is a group, then this element must be C. This must be A. However, A times C is B. So it's not A. It's B. So therefore, this subset must contain B. But now this subset contains all the elements of G. So this is the same group as G. So it's not a proper subgroup. So if any subgroup contains the element A, it must be equal to G itself. So let's consider the next possibility. So suppose if we have a subset that contains the identity element and B. So is this closed under multiplication? So EB and EBB. So if this is a group, then this element must be E, because in every column all the elements must be different, so the only possibility is E. So let's look at this table. B times B is C. So it's not E. Therefore, this subset is not closed under multiplication, and we have to add the element C. Now, if we add C, Then let's see, b times c is a. Now we have a, and c times a, b is a, and c times c is e. So now we have a, and this subset is not closed under multiplication, and we have to add a, and that's equal to g. So if any subgroup contains the element b, it must be equal to g. Now let's try another possibility. Suppose, let's write it here, a subgroup contains the element c. So is this closed under multiplication? Is c, this is c. So if it is closed under multiplication, this element must be equal to e. So what is it? So c times c is e. Yes, indeed it is e. So this is closed under multiplication, and clearly c is its own inverse. So c squared is equal to e, so that means c inverse is c. And this is closed. And so this is a proper subgroup of G. And we have tried all possibilities, and this is the only proper subgroup of G if G is given by this Cayley table. Next example is made of 2 by 2 matrices. Let's define G as a matrix of this form, A, B, minus B, A, where A and B are real numbers, and A squared plus B squared is not 0. So that means at least A or B, one of A or B is non-zero. Okay. Of course, they can be both non-zero, but they cannot be equal to 0 at the same time. Okay. And this G is a group under ordinary matrix multiplication. To see this, let's see. So AB minus BA times CD minus DC. So this is AC minus BD, and AD plus BC, and minus BC minus BC minus AD, and minus BD, AC. So this can be written as AC BD AD BC minus AD plus BC. So that is negative of this element, and AC minus BD. So this and this are the same element. So this belongs to this group, this set G. So this set is closed under matrix multiplication. And obviously the identity element is 1, 0, 0, 1, and this belongs to G because this element, this and this are same, and this are 0, so negative sign doesn't matter. And also the inverse element is so if we have AB minus BA, its inverse is given by A squared B squared, what is it? A minus B, BA, right? To see this, just multiply this with this original matrix. Let's see. So just for the sake of simplicity, just ignore this factor for the moment and calculate this, and we have a squared plus b squared and minus ab plus ab, so that's 0, minus ab plus ab, that's 0, and minus b times minus b, that's b squared and a squared. So if we divide everything by this factor, then this is 1 and this is 1. So that is the identity element. Therefore, this is the inverse matrix of this. So, and of course, the inverse matrix here has the form of the same element on the diagonal, and off diagonals are negative of each other. So this again belongs to this set G. So the inverse element is an element of G. So of course, matrix multiplication is associative. So this G is indeed a group. Okay. Now consider the subset of G consisting of 4 matrices. 1, 0, 0, 1, that is the identity matrix as we have seen. Negative 1, 0, 0, negative 1, and 0, 1, negative 1, 0, and 0, negative 1, 1, 0. So this is a subgroup of G. Okay, let's see. Let's put this as E, A, B, C. To see this is indeed a subgroup of G, then we just construct the Cayley table. So E, A, B, C, E, A, B, C. And since E is the identity matrix, here we have E, A, B, C, A, B, C. And let's see. A squared is negative 1, 0, 0, negative 1, negative 1, 0, 0, negative 1. That is this, so that's E. And AB is 0, 0, and negative 1, 0, and 0, positive 1, and 0, 0. So that is C. And this should be B. You should check. And BA is 0, 0, and 0, negative 1, positive 1, 0, and 0, 0. That is C. And B squared, 0, 1, and 0, 1, negative 1, 0, 0, negative 1, 0, 0, 0, 0, negative 1. So that's A. So B squared is A. And BC should be E then. And A, so this should be B, and A, B, C, this should be E. And this should be A. So you should check this. And from this table, uh, well, actually, to construct this table, we assume that this subset is closed under multiplication, but you should check really. Then construct this Cayley table and see this set indeed is closed under matrix multiplication. Then from this table, we can see that all the inverses are, of course, in this subset. So this is a subgroup.